The next rule for deriving functions involves deriving inverse functions. Before we get into deriving inverse functions, this video is serving as a quick reminder of inverse functions, which you learned about last year in pre-calculus. All right, inverse functions, we know that two of them are inverses if they reflect onto each other over the line y equals x. All right. So if we go to example 33 quickly, right, it says graph e to the x and the natural log of x and show that these two functions are in fact inverse functions. All right, now e to the x, we recall, is always positive. When x is very, very small, like negative 100, e to the negative 100 is very close to 0, but not actually 0. So it's just above the x-axis. And this holds true for all of the negative values of x. But then as soon as we get to 0, we have e to the 0 power, and anything to the 0 power is 1. And so we have to go through the point over 0 up 1. And then we have, when x is 1, we have e to the first power. We know e is about 2.78, or 718 rather, so we know that at that point we are somewhere in this vicinity, and because it's an exponential function, it skyrockets rather quickly. So this is the graph of e to the x. The graph of the natural log of x has a restricted domain. We cannot take the natural log of a non-negative number. So there is no graph of ln to the left of or on the y-axis. But in fact, it begins just after the y-axis, and it comes up and it skyrockets rather quickly. The natural log of 1 is going to be 0. The way that you learned, and we've learned about natural log functions, or log functions in general, is that the log of any base of 1 will be equal to 0, because basically that's the same thing as saying what number to the 0 power is 1. Any number is. So all of our logarithmic functions are going to go through the point over 1 up 0. And at that point and thereafter, the graph continues to increase, but does so at a much smaller increments. So what ends up happening is we get a graph which is going like so. And this graph right here in black, this is the natural log of x. And this graph up here, we said, is e to the x. And then if we look at the line y equals x, that would be this line right here. And we can see that the red curve and the black curve are mirror images of each other over this broken line of y equals x. All right, so in essence, if we were to take our paper and we were to fold it over, the red ink would match up right on top of the black ink. All right, these are inverse functions, and their graphs have to be reflections over the line y equals x. But let's say we're not dealing with graphs. Let's say that we're dealing with just formulas for these functions. So if two functions are inverses of each other, if their composition is equal to, or can be simplified to, x. Okay? So let's scroll down to example 34. And it says, show that these two functions f and g are inverses. Okay. So if these two functions are inverses, that means that f of g of x must be equal to x. And in addition to that, it doesn't matter which function we plug into the other. In other words, g of f of x should also equal x. We don't have to do both. We could just do one. So let's do this. Let's plug g into f. All right, so we want f of g of x. That means we're going to take the g function and we're going to plug it in for all x's in f's function. So we are going to have our fraction bar with 4 in the denominator, and plus 5 will be at the end of the numerator. But instead of x being cubed, it will be g of x being cubed plus 5, like so. Well, what's g of x? It's this cube root function. So we have the cube root of 4x minus 5 being cubed. This cube and that cube are one and the same, plus 5 all over 4. Well, let's simplify this. We have a cube root being cubed. What do they do to each other? Exactly, they're going to wipe each other out, which means we now have just 4x minus 5 plus 5 over 4. The cube root and the cube, they eliminate each other. What can we now eliminate here? That's right, the 5's. Minus 5 plus 5, which means that we have 4x over 4, and we all know that that simplifies to x. So we've taken the composition and we've done the mathematical steps to show that the composition is equal to x. This also proves that these two functions are inverse functions. What if we don't have a formula? What if we just have various inputs and outputs of a particular function? All right. Well, the way that inverses work, in the same way that they worked here on the graph, is that the x values become the y values and the y values become the x values. All right. Take a look at this specific point right here. E to the x goes through the point over 0, up 1. Natural log of x goes through the point over 1, up 0. All we do is we change the x, over 0 and up 1, and then this is over 1 and up 0. We just change the x and y values. So if we go down to example 35, let f be a continuous function, and here are some values. Find the value of g of 4. Right. So this right here is saying that when we plug 1 into f, we get 4. f of 1 is equal to 4. And this right here is saying that f of 2 is equal to negative 3. And then this one right here is saying f of 3 is equal to negative 1. You get the idea. Okay. So we're interested in finding the value of g of 4. Well, there is no g here. Okay, but we do know that g and f are inverses of each other, which means that all of the f values, the y values, if you will, now become the x values, and all the x values now become the y values of the inverse function. All right, so we just swap columns, basically. We're interested in g of 4. Well, when x is 4, g is 1. So g, oops, let me get that on the screen, g of 4 is equal to 1. Okay. A lot of people want to say, oh, well, x, here's the 4 right here, so g of 4 is equal to negative 2. That's not the case. G of negative 2 is equal to 4. F of 4 is equal to negative 2. Okay. But notice right here, if f of 1 is equal to 4, and g and f are inverses of each other, then g of 4 must be equal to 1. We swap the x and y values.